All right, we are dancing here today, it looks like, so it must be a new topic. You see one of the vibration modes in the infrared spectrum there for ethylene. This will be the topic of chapter 13 here. By the way, that video up there, the image is of course from CHEM351, and you can get to that, of course, it's a free online thing. It's under structure and bonding, and then vibrational modes, molecular vibrations in the IR. So that's what we're looking at there. Those are bending modes. We'll look at bends and stretches. That's a topic coming up in this chapter. But what we have today, of course, is that chapter 13, both mass spectrometry and IR spectroscopy. This is for Monday, March 30th. So homework 13 is due tonight. We'll be finishing this chapter in this one presentation. That means we'll be starting NMR chapter 14 on April 1st, Wednesday there. So stay tuned for that. Now, what do we mean by spectroscopy and characterizing molecules? So the outline for this chapter, let's go over that first. So you see what we're going to do here. This is different. This is a departure from our usual chapters, where we've been talking about reactivity. Now we're talking about characterizing molecules. So we're measuring molecules, we're back to structure, trying to figure out how we know what we have molecule-wise. And the two first techniques we're going to use mass spectrometry. We're going to determine the molecular weight of the molecule. There'll be some fragmentation patterns, but that's the information we get from mass spec, or MS there, just the molecular weight. And then IR spectroscopy, we're going to establish the presence or absence of specific functional groups, looking at the different vibrational modes, the bond stretching and the bond bending modes. And we'll have to define what that means exactly. So first mass spec here, we're going to be looking at the parent ion. This is the molecule itself, knocking out one electron, giving a cation here. What the machine actually measures is the mass to charge ratio. Little m means the mass of the molecular weight in atomic mass units, and Z is the charge, okay? So that's what we need to define. What we learn here is the molecular weight. If there are isotopes, remember those can have different atomic mass units, right? Different numbers of neutrons in the nucleus, so we can see those by mass spec. We can also see fragments. The molecular ion or the parent ion often fragments to give other stable ions. The base peak sometimes is not the molecular ion peak, it's a major fragment peak. Okay? We also have the nitrogen rule, which means if we have one nitrogen or an odd number of nitrogens, the parent ion or the molecular mass, the molecular weight of the molecule will be odd. Okay? If it's just carbon, hydrogen, and oxygen, the molecular masses, amazingly, are all even. What that means is all the fragments from that even mass for a molecule, they're all odd. So it kind of switches back and forth. Halides, chlorine and bromine, which are very common, have these stable isotopes, chlorine 35 and chlorine 37. They're in a ratio of 3 to 1. Bromine 79 and 78 are 1 to 1. Here, so we can easily tell alkyl halides in the mass spec from that. Fragmentation, I'm going to downplay this as much as I can. The molecular ion peak often fragments and gives other stable cations. Acylium ions from carbonyls, ketones, we'll look at that, maybe alcohols via alpha cleavage. There are other types of mass spec. We'll mainly look at just electron impact mass spec, which gives you the molecular weight there. There are others that can give you the high resolution mass spec, which is the exact mass for a given molecular formula, and also separating the molecules via chromatography, or GC, gas chromatography, and combining it. There's often machines that combine the two techniques, GC, MS. And electrospray ionization. There are some other types of ionization I might mention just very briefly. Okay, and then we also have IR, or infrared spectroscopy. And the different terms here. Spectroscopy means a process where the molecule is actually absorbing radiation, okay, and going to a higher quantized energy level, and then decaying back down. that in mass spec, we're not irradiating a sample and seeing a decay back to the ground state. We're just counting ions, so it's spectrometry. Okay, so if you're wondering what the difference is there. But IR, infrared, in this region, these are processes of 1 to 10 kcal per mole, which involve bond stretching and bond bending. So we're talking about bond length distortions. They're kind of like springs. Two atoms can vibrate or oscillate, changing the bond length between them. Or we can have a theta, a bond angle, that involves, of course, an angle between three atoms, and the deformation of that theta angle is called bending. Okay, the higher energy event is the bond length distortion. We'll define where that occurs and what goes on there. But yeah, stretch and bend, and we're talking about inverse wave numbers or inverse centimeters. And that's a strange unit. I'll try to define that and make that clear. But the bending region is 400 to 1400 inverse centimeters. That's the bend region. 1200 to 4000 inverse centimeters is the stretch range. This strange unit, inverse centimeters, cm, stands for centimeter, right? To the -1, which means it's in the denominator, which means it's directly proportional to energy. So we'll have to look at the Planck's energy expression, where energy equals h nu. Nu is referring to frequency. Frequency and wavelength of the radiation are inversely related through the speed of light constant. We'll define that hopefully carefully. There are things that affect where in this region these transitions occur, and depends on how strong that bond is. By Hooke's law, you can see that the mass of the atoms involved in the bond is directly proportional. The lighter atoms generally oscillate at higher frequencies, require higher energies. The change in the dipole moment of that oscillation has to do with how intense the signal is in the IR. So we'll look at that change in the dipole moments. Here are the ones you need to know. Alkyl CHs, 2900, carbon-carbon, around 14, carbon-carbon double bond, 1650, triple bond, which is higher in energy, 2200, OH, a very stable bond, over 100 kcal per mole, 3500, and it's very broad. We'll define how intense these signals are. Aromatic, carbonyl, that's probably the most important one along with alcohols, OH, 1700, and very strong, intense signal. Then we got carbon-nitrogen double bonds, carbon-nitrogen triple bonds, which we've seen in nitriles, right? Cyanides forming different nitriles. 2250, and those really stand out there. The triple bond, 2200, and a little bit higher, the 2250. We'll have a couple applications here: penicillin, periplanon, the molecular formulas, degrees of saturation, and what functional groups are present. So we use different combinations of analytical tools to determine the structures of different compounds. So that's the outline. Before we get into the details of mass spec and IR, let's go over here and look at some practical examples. Why is this important? Why do we need to know what the structure is, and how do we get there after all? And what are some examples of molecules we can figure out? Well, about 10 years ago in Germany, there were a bunch of people admitted to the emergency room, and a few of these people passed away. And they were trying to figure out why, what was in their blood, and they had all sorts of different symptoms, and different people showed different types of overdoses, and it wasn't meth, and it wasn't speed or any other, it wasn't heroin. It was a different effect that appeared like they overdosed on marijuana, which is very unusual. That normally doesn't occur. But if you have very high doses of marijuana or THC in the blood, you can actually hallucinate and have high blood rates, have high heart rates, whatever. And that's what actually they're seeing from these people who passed away. And they couldn't figure it out, but they took a mass spec of organic compounds isolated from their blood, and from the mass spec, they could see a molecule that had a mass of 341. And they kept seeing that peak in the mass spec, thinking, well, what molecule is that? Well, they have a lot of known mass spec data for different drugs, and nothing really matched this 341. And they thought, well, did they switch up these digits? Did they really mean 314? Because the symptoms showed similarities to marijuana, which is tetrahydrocannabinol, which has a mass of 314. So you can see where the confusion was. Well, they finally isolated enough from blood samples to get enough of this material purified and took an NMR of it, and it turned out not to be THC, but this compound right here, which is a ketone with an naphthalene and this indole functionality here, and an alkyl group off the indole. This is a known compound that binds to the cannabinol receptor even more tightly than THC, and this was produced actually at a university in the United States, and this person was studying compounds that bound to the cannabinol receptor and those effects in the brain and then the neurons. But this compound became known and started to be abused. There were labs around the world that started to make this material. They knew of the crossover effects that had similar effects to marijuana. But anyway, it's only figured out using mass spec and then finally NMR to figure things out. Now let's look at this molecule down here, TNT. You're probably familiar with that. You may not know what the acronym means. What? Trinitrotoluene, explosive reagent. The mass here is 227. The molecular weight, if you add up all the carbon, nitrogens, and oxygen, hydrogens there, you get to that mass. This is, of course, a detonation hazard, causes explosions, can be used to make bomb materials, whatever. Terrorists have used this for a long time, very well known, and initial screenings at the airport were based on the IR of this compound. And it gives very intense IR signals, and they used to have their machines calibrated for that. Well, the terrorists are smart guys. They switched over to this compound, which is the peroxide acetonide of acetone, or TAP. And this has a different molecular weight of, let me get that on here, 222. And it's also not active in the IR where TNT is. So the shoe bomber and a couple of these other terrorists right after 9/11 had switched over to this molecule right here. The scary thing is you can make this directly from acetone and peroxide and strong acid. So this is a real hazard, and law enforcement, of course, security people now use mass spec, a link to that ion right there, to make sure there's no trace of this material on any stuff coming in and out of airports or different places. Anyway, these are a couple things that have a medical application here between spice and THC, and what a law enforcement thing here. So people involved in forensics are interested in analytical tools. Natural products like THC coming out of a plant. Oftentimes we isolate new natural products that have new properties, have new structures that need to be figured out, and we'll have to do that to determine things. So let's go back over here and begin to talk about mass spec and how this relates to operations that organic chemists do. So when we make a new molecule, so here's a starting material here by thin layer chromatography. We see a distinct spot as it moves up this silica gel plate here. And we get a new product here from the reaction, and it's a distinct spot. Well, we know it's a new spot. We have to purify it and then characterize it. Well, here's the process we usually go through. We never use one analytical tool in isolation. It's always a combination of techniques. So I have to purify it by chromatography here. If it's a crystalline solid, that's good. That can be used to help purify it. Or if it's a liquid, we can distill it to purify it. And then we use NMR, IR, and mass spec routinely. If it's a good crystal, we can do X-ray crystallography. In the solid state, it's bombarded with X-rays, and that diffraction pattern can be used mathematically to reconstruct actually the 3D coordinates of the structure of the molecule. But in normal practice, we use IR, mass spec. We get two important ideas there, right? We get the molecular weight, okay? And we get functional groups being present or absent in IR. And then NMR really nails it down. There's three key things there that we learn about: the types of atoms involved, how many are in the signal, and how many neighbors of what type that those different atoms have. So that's really a very powerful technique. And it's related to MRI, which is the medical imaging technique. Involves these magnets and a lot of specialized electronics that we'll get to in chapter 14. So stay tuned for that. So there's a lot of reasons why we need to know the structure of a molecule to figure things out. Now let's first look at mass spec. So what we're looking at here is the actual key components of the machine. So this is a mass spectrometer. Here's where the sample is introduced, and it flies into this tube here. Now this tube is completely evacuated. It's sealed, and it has a very powerful vacuum pulling on the material. The sample comes out of the sample chamber and gets ionized here by an electron beam, a filament here. This is called electron impact, or EI ionization. And there's some initial focusing slits here that kind of eliminate real high molecular weight stuff or low molecular weight stuff. And it begins to fly down the tube here as a stream of ions. So it's ionized here as it comes out of this point. Now the detector is negatively charged, the cathode tube. So this negative charge pulls these cationic species from the sample through the tube, and then we focus the sample beam based on the molecular weight or the mass of the material. And you can change the electronics of the focusing magnet so that the higher molecular weights aren't deflected as much as the lower molecular weight ones. And then these ions hit the detector plate. It's a cathode plate, which actually just counts or how intense those positions are as it hits the detector. And these are calibrated with a known molecular mass molecule. And then a computer regenerates or counts those ions here. So we have the intensity of the signal here in the y-axis, and then we have the molecular weight of the material coming out here. We often see a lot of these straight lines as they come out there. Now let's look at the specifics of a specific molecule. So in the y-axis, we have the relative abundance, or the intensity of that peak coming out, and that's normalized by the computer. And like I said, this is calibrated initially with a sample with a known molecular mass. And then what we see in the x-axis is the mass to charge ratio. So typically these are just monocationic species we're looking at. And they have to be charged to fly down the tube and hit the detector. Anything that's neutral will just sit there or be pulled out by the vacuum. What flies down the tube and hits the detector are the charged things. So here's the sample. What do we have? We have methane. Okay, we'll start very simple, CH4. And you can add it up. What carbon? What's the atomic mass unit of carbon? The C12 isotope, the most abundant one. That's right, it's 12 atomic mass units. And that's what we see in the periodic table. Now, what do we see in the periodic table? For carbon, we see a mass of 12.011 atomic mass units. What's up with that? The definition of 1 mole of carbon-12 isotopes weighs exactly 12 grams. So how do we get to this 12.011 mass in the periodic table? That's right, it's the isotope that's abundant also. Well, not too abundant. C13 has an abundance of 1.1%, and so that adds that 0.011 to the weighted average that we see in the periodic table, 12.011. But in mass spec, we see the exact mass for a molecule. So here it is. We've got 12 for the carbon, and then 4 for the hydrogens, comes out to what, 16. And there it is. We call that the M peak, or the parent peak, or the molecular ion peak. Its mass to charge ratio is 16, exactly. And you see this little +1 peak. What's that again? That's the C13 isotope of methane coming in there. And what are these peaks just below here, losing 1 atomic mass unit at a time? Well, that's what we're explaining here. They begin to fragment. This electron impact ionization is over 1,000 kcals per mole energy. Is that high enough to blow a molecule apart? Yes, it is. So these things begin to fragment as they ionize to be able to fly down the tube. Enough of them stay intact to hit the detector, and we can see what they are. But here's the fragmentation. So we see, well, here's your isotope thing I just mentioned there. And look at the abundance of these lighter ones here come about because of the fragmentation. So how do we knock out an electron to form the cationic part? These electrons are all in bonds, so we're pulling one electron out of a sigma bond here. A lot of times we ionize a lone pair on a carbonyl oxygen or on an oxygen and an alcohol, or a lone pair on nitrogen. But we can also knock out an electron with this kind of energy directly there from a sigma bond. And what we have then is the ionized state. If we lose a hydrogen atom, you see we drop down to the methyl cation, which is what, 15? That's right here. We only see that in the vapor phase, in the tube there, not in solution. Remember I told you the methyl cation would be the least stable thing. If we lose another hydrogen atom, that just comes off with its, as a neutral atom, that leaves behind the methylene radical cation. That's 14, it's there too, it's less abundant, and so on. We can go down to the methine cation, and then down to the atomic carbon cation, which is also very, very tiny there. But again, that's the mass spec of methane there. Let's look at some other more complicated ones here, and this is for hexane. So you can add it up here. What's the expected molecular weight here for the parent ion or the molecular ion peak? It adds up to 86, which is what? 1, 2, 3, 4, 5, 6 carbons. What's 6 times 12? 72. 72, and then how many hydrogens do we have? 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So add that in there, we get up to 86. So that's the expected molecular weight. And notice it's even. We don't have any nitrogens there. So it's the even mass there. But what's this? The base peak is 57. That's the highest, most abundant one. That's because this thing fragments to lose a methyl group, or I'm sorry, an ethyl group. We'd have to lop off 2 carbons and 5 hydrogens to get down to 57 there. And this fragmentation thing, I'm going to downplay that. We're going to show you or tell you where the molecular ion peak typically is. It's always the furthest one up here to the right, but oftentimes we have these little isotope peaks also here. You can see the 87 peak for the C13 content. It's probable that one of these is C13. You can see it's a little more abundant there. The more carbons you have in a molecule, the more abundant this little +1 peak is. So that's called the parent +1 peak, which is 87. Whereas the molecular ion peak of this guy just ionizing, losing an electron out of a sigma bond, then all these atoms as a cation flying down the tube is the 86 peak there. All right, let's move on to a couple other samples here. So these are diagnostic for other types of molecules, and you can see here pentine. Add up all the atoms there in pentine. We got 1, 2, 3, 4, 5 carbons. So that's what, 60 plus the 8 hydrogen. There's our molecular ion thing. And they typically lose 1 proton off here to give the M-1 peak as the most abundant one. So you see there, 67 is actually the base peak, the biggest one. It's called the base. The one that's the intact parent molecule, the parent or the molecular ion peak, you see is a little less abundant there. Pentine, a little bit different story. You see the molecular ion peak more robust there, 70 there. And notice what, we have 2 more hydrogens here. This one loses 2 hydrogens relative to this, so pentene is 70. And then pentane has 2 more hydrogens, right? So it's at 72. And they all fragment and get these other base peaks down there. And we'll have to look at that in a little bit more detail. Here's this nitrogen rule I mentioned. A couple molecules here. These are both opioid painkiller molecules. You've probably heard of fentanyl, and maybe you've heard of MPPP. This piperidine compound here. They all mimic the structure and the activity of morphine. They were all designed based on the morphine structure, which is a naturally occurring one. These are both synthetic compounds. What do you see here? 1, 2 nitrogens. So 2 nitrogens here in the molecular formula. Add it all up here. 12 for carbon, 1 for hydrogen. What's 14? Look in the periodic table. Nitrogen is 14 for each one. And oxygen is what? Atomic mass of 16 for O16 there. And add that all up, it's 350. That's an even number. Why? It's got nitrogens in it. Oh, it has 2 nitrogens, so that means it's back to even. If it has an odd number of nitrogen, then it's always an odd parent peak or molecular weight. MPPP here has just one nitrogen, so what do we expect? Yes, an odd mass. Okay, so you can tell a little bit about nitrogen containing. A lot of drugs have nitrogen. That's a good way to keep track of it. Okay, another thing to look at are isotopes from stable halides. I mentioned this in the outline, so here's a specific one, isopropyl chloride. And you see up here, we see an M peak at 78, and we see an M+2 peak. Those are the exact masses for the ratio 3:1 of the isotopes that are abundant here. This is for chlorine 35 here, the one at 78. And what's the one at 80? That's right, it's the chlorine 37 isotope, which has 2 extra neutrons in the nucleus, so it has 2 extra AMU or mass units there. And if you see a ratio of 3:1 up here at the top, you probably have a chlorine. Okay? Notice they're still even, so the nitrogen rule applies here. There's no nitrogens here, so these are even though they're halogens now. Then we have isopropyl bromide here. It's heavier. These are the 2 parent peaks up here, the M and the M+2 peak. And they're in a ratio of 1:1 because that's what bromine has its abundance on Earth here. It has the 79 isotope and the 81 isotope. And they're 2 mass units apart from each other. The weighted average appears in the periodic table. Okay, so you can see that from that abundance of being 1:1. But if you see this 1:1 peak up here, it's the highest molecular weight thing that you suspect to be the parent. If it's 1:1 and it's M and M+2, you probably have bromine. If it's 3:1, you probably have chlorine. So that's a good way to tell and keep track of that. All right, let's see. Before we get back into fragmentation, let's work a problem here. So let's come back down to the chalkboard. And let's see how we use this information to figure out beginning ideas about what's the structure of a molecule. So let's say in the mass spec, we see an ion of 86 mass to charge ratio, okay? And we're told that that is indeed the parent peak, the M+ peak, okay? 86. So what can we learn about that and figure that out? Well, we're organic chemistry, so how many carbons might be in that 86? Well, it's 12 per carbon, so you can already propose some reasonable structures here. And whatever carbon makes up the mass, then probably hydrogen needs to be in there, or maybe oxygen. Do we have nitrogen? If we had nitrogen, we'd have to have 2, or maybe 4. But in a practical sense, let's see, 86. How many do we have here? Well, let's propose something. C6H14. What would that be? Well, 6 times 12 is what again? 72 plus 14. Yeah, 86. That would work out, right? How many rings or chains might we have here? 6 and 14. Remember the degrees of unsaturation that we talked about before? Looking at a molecular formula. How many rings or chains would we have here? 6 times 2 plus 2. Oh, that's the max. So no rings or chains. So could we propose a structure? Yeah, what would it be? Hexane. We're just looking at it. Would that be the only one? No, we'd also have this. And maybe some other constitutional isomers, but those would be consistent with this peak here. Is that the only one for 86 though? Let's see. If we had C7, what would that be? What's 7 times 12? That's what? 84? And then we'd only have what? 2 hydrogens? Is that a reasonable formula to propose for an 86 ion? Probably not. You can probably draw something. It'll look really crazy and really unstable, but this is way unsaturated. So this isn't a reasonable structure. What we might want to consider doing is going lower. How about C5? C5, that would be 60, and then what? Maybe hydrogens? Well, hydrogens, so how many would we have to have? C5 would be 60, and then we'd need what? 26. Well, what else could we have there? Maybe carbon, and how about an oxygen? Okay, so that would be what? 60 plus, how much for an oxygen? 16, so we're up to 76. And then what? 10 more, yeah. So that might make some sense. C5H10O. What type of structures could we expect there? How many degrees of unsaturation might we have in it? And this makes sense, right? 5 and then 10 here. But degrees of unsaturation, what the max for 5 would be, what, 12 hydrogens, right? If we were fully saturated, but we're what, unsaturated here. So it's 12 minus 10 divided by 2. Remember how to do this degrees of unsaturation thing. So how many do we have here? We have one ring or one double bond, okay? And there's a couple structures we could draw there, right? Let's see, what would they be? Oh, how about just a ketone? And does this have one unit of unsaturation? Yeah, it has one double bond right here. Count them all up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. Yeah, so that would work for a molecular ion of 86. And look, it's very different from hexane, isn't it? We can go to the exact mass and figure out which one is which. But right now, just on the molecular formula, low resolution, this one fits it. Is there another structure here? Yeah, be this one. Okay. That would also fit for the mass. Are there some other formulas we could look at? Well, there's also this one, C4H6O2. And there we have how many degrees of unsaturation? We have 2, okay? So 4 would be the max of what, 10? 10 minus 6, 4 divided by 2, 2. We have 2 oxygens here, so you might want to think about, oh, how about an ester? Is that 4? 1, 2, 3, 4. Yep. And how many hydrogens? 1, 2, 3, 4, 5, 6. Yep, there it is. And 2 there. And there's some others you can draw there. But this just gives you an idea. Mass spec tells us the molecular weight and gives us an idea of what the structure might be. But what would we have to do to figure these things out? Yeah, we have to use IR. These have different functional groups. And we'll see, combine that with the story here in a second. And of course, NMR can then determine the differences between these very clearly. So let's look at fragmentation a little more here, going up to the graphics. And again, you have all these graphics on Learning Suite, and they're from your book, most of them, but you have all these on Learning Suite. So I have my PowerPoint presentations there. And this is back to hexane, the one we were just looking at. Yeah, there's our 86 peak. And our molecular ions up here, we already talked about that. Well, what's this base peak, this 57, the most abundant one? Well, if we fragment off two carbons here, if we fragment that carbon, we get to that. But if we knock off another carbon, which means we're taking off 2 carbons and what, 5 hydrogens, that's minus 29 atomic mass units from there. So yeah, this base peak right here, 57, is loss of an ethyl radical, you could say. And we're left behind with what, the butyl cation. Not this cation, this pentyl cation is 71. Is it there too? Yeah, it's right there, a little bit. It's a little bit more common on these straight chain molecules to lose an ethyl radical and generate, but in this case it would be this butyl cation, which is right there, okay? And then these other peaks right below are losing more hydrogen atoms from these cations. Fragmentation can get very complicated. I don't want to get into that. Most problems will give you the molecular weights, and you can see how it's going to work. But it's good for you to see how it is. Oh, and yeah, here's a little more detail on that. The butyl, the propyl, and the ethyl cation. And those are the only ones we see. It has to be cationic in order to see. There's actually reverse charge mass spec where you look at the anions, and there it's not a cathode ray, it's an anode ray detector, which pulls down anionic fragments. That's the unusual mode. The easier mode to detect and look at are the cationic ones hitting the cathode ray detector. But yeah, here's our poor, very low abundance molecular ion. It's always the one furthest to the right, okay? Usually, you might see some little isotope peaks there. but then the fragments are always to the left of that lower molecular weight. Okay, hopefully that's clear. Don't want to spend too much time on fragmentation. Here's fragmentation of a ketone. It's called alpha fragmentation. This is very common to lose an electron out of a lone pair. Here's the molecular ion, which is 100. You see it there. But then it fragments. The most abundant one is this 57 thing. It's called an acylium cation. We'll see that later when we look at acyl transfers in 352. Some of these fragmentations have to do with reactivity. You can kind of tell how stable things are and how the fragments form. And you can identify some other fragments here. But here's your molecular ion peak, your parent peak. And this is your base peak, the biggest one there. And I think that's all I want to say on that. You can look through that. Oh, yeah. I added some alcohol fragmentation here. And some of this makes sense if you want to look at how they fragment there. And this is a more detailed thing in an advanced book. But it kind of gives you a little more flavor for fragmentation. We will give you the molecular ions and use it to help solve simpler problems, okay? Like I said, this can be used in conjunction with other analytical techniques, including separation or purification via gas chromatography. That's what GC stands for. This is a tube here, and in the tube, it's packed with a solid support that's immobile. Usually that's silica gel or very fine sand or a gel-like material that does not move down the tube. Okay, it's the immobile phase. And your sample's injected in one port here, and usually it's heated up or vaporized. And then your sample begins to travel down the tube, and depending on its polarity and molecular mass, it comes out at different times here. And then the export tube out of the GC goes directly into the ionization port of the mass spectrometer. So these are often linked together. And it's very routine analysis for known compounds. If you work in a chemical analysis lab in a hospital or law enforcement, whatever, they have all this type of analysis there. And here's our ionization. Here's our flight tube that can be focused by a magnet, or the time of flight sometimes used to separate the ions. Then they hit the detector, and of course the computer compiles it, and then you get out the data here. Here's what the output of the GC looks like. So the peak intensity can come out here, and then each one of these ions, as they come out, this one would come out first, and that goes into the mass spec. This one comes out next, that's ported into the mass spec, and then here's the last one. These are called the retention times, so the time here, and the x-axis is just the duration. Usually it's minutes, sometimes it's quicker, depending on what type of sample you're trying to separate. I think I've got a more complex, oh, back to THC. So THC, this is the compound out of marijuana that gives you the high. This is the bad actor. This is one we try to eliminate. Cannabidiol is the compound that has this ring open right here. They actually have the same mass, but they have different fragmentation patterns and different NMR signals. And CBD is the one, like I said, the ring open one here that controls pain and brain seizures. So that's the beneficial one that a lot of people are interested in. CBD oil and medicinal marijuana, that's the medicine. THC is not the medicine. But here you can see the parent peak, yeah, 314, no nitrogens, and there it is there. It has a lot of carbons, 21 carbons, so it's more abundant to see these little +1 and a +2 isotope. That's an ion where there's 2 C13 atoms in there, okay? So oftentimes you see a little bit thing there. And the fragmentation, I'm not going to explain that, but that can be analyzed by GC mass spec, as well as a bunch of things. So here's a panel of 20 known drugs. You can read through those and see which ones you might know. Here is the gas chromatography as they come out in minutes. That's the retention time, and then just the abundance of these peaks. Each one of these peaks can be shunted into the mass spec. Mass spec is very sensitive. You only need a picomole of material, less than a picogram, and you can get a response and see the ion. This is very high sensitivity technique. Anyway, there's some examples of that. All right, let's get into IR. And this is infrared spectroscopy now, not mass spectrometry. Need to keep those straight. And why? If you talk to spectroscopists, They're people who are interested in using this analytical tool that uses electromagnetic radiation. So here's our old friend, the photon, or light. And as light propagates through space, it has particle-like character. Yes, it has a mass. It's infinitesimally small. It can be measured, though. A photon of light coming from some source, the symbol is h nu, Planck's constant times the frequency. Planck's constant is a very, very tiny energy unit, but it is quantized at the atomic, very small level. These are all quantized events, so we'll talk about that. But as it propagates through space, it generates two fields that can be measured. A electrical field here, which is the red vector quantities as they oscillate, as it propagates through space. The wavelength is the distance between the two peaks, or between the two troughs, however you want to keep track of it. And then there's a perpendicular field that's set up by this propagating photon, called what? A magnetic field. And the manipulation of these electronic and magnetic fields is the basis of all the electronic devices we know and love, okay? And this is just the last 100 years or so that we figured this out. If you want to read about the religious components of light, and you can do that in DNC 93, and read about light and all the scriptures that talk about light, and that's great. It's a very profound topic religiously, and it's a very profound topic scientifically here. The frequency, or nu here, is the number of peaks per second coming past a detector, okay? The speed of light is the speed of the propagation of that particle along a pathway, but it's how many peaks or troughs come by the observer that's what the frequency, or events per second. That's a different idea. We're counting up the peaks or the troughs. Those can be detected different ways. But that's distinct from the speed of light, which is c, the constant, which is what, 3 times 10 to the 8th meters per second. That's a constant here. Frequency is related here to speed of light over the wavelength, which is the distance between two peaks. So basic physics, you should have a feel for that. We use all different types of radiation to characterize molecules. Gamma rays are the very high energy end. And these are inversely related, right? So this is high energy, high frequency up here. This is what? Long wavelength, low energy down here. Radio waves, your FM dial, whatever down here, your cell phone, all that stuff's way down here. Microwave, there's your magnetron and your microwave oven. That excites the rotation of water molecules. So that's what that frequency is linked to. Infrareds, that's what we're talking about here. This is that 1 to 10 kcal per mole event, bond stretches, bond bending, angle bending. Visible, this is the only region we actually see with our eyeball from the violet region, and then higher frequency, higher energy is ultraviolet, beyond the purple, that's what that means. Infrared means below the red, okay? Lower in energy than the infrared thing there. X-rays and gamma rays are very high ionizing radiation. A lot of bad things happen there. X-rays are on the dimensionality of the wavelengths of the bond lengths of different molecules. That's why the diffraction patterns of X-rays can be used to determine the 3D structure of a molecule. All right, here's how a spectrometer works. Everything you've ever wanted to know about analytical chemistry is right here. We use different wavelengths of electromagnetic radiation. Here's our source here. We can vary the frequency or the wavelength, doesn't matter. That creates a spectrum. We can sweep those frequencies or vary it depending on the source. Goes into a splitter. One beam comes off here. That's our reference beam. It stays linked to what the source is here. And then another part of the beam is shunted into the sample. So here's the sample tube that can absorb some of that radiation, okay? So what the detector sees here is we just measure the difference between the reference beam, which stays, unabsorbed, and the sample beam, which is absorbed at specific frequencies. And that gives us our absorbance, okay? So what are we talking about when we say absorbance? So come back down here to the board just real quick, Isaac. So what are we talking about? How can a molecule absorb energy we talking about here? Well, here's energy, and here's the ground state, okay? And whatever that ground state is, our molecule's happy, it's sitting there, okay? But if we excite it or apply some energy, we can go up to the excited state, okay? And our molecule absorbs this frequency, whatever it might be, of light to get to this excited state. So what do we mean about an excited state? Well, it's some sort of process that's sympathetic or corresponds to the energy that's being applied to it. It has to have this sympathetic or corresponding response to that frequency in order to do something. All the other frequencies can be invisible, okay? They will just go through the sample and not be absorbed. But when it has a sympathetic frequency here that's absorbing it, either a bond length distortion, which we're going to talk about in stretching bonds in the IR, or deforming a theta angle and bending the bonds. So here's the energies we're talking about in the IR, bond length. So two atoms just oscillating like that. Well, you know, most of the time it was just sitting like this, but when it feels that applied energy that corresponds to that frequency of oscillation, it will absorb that energy. No other frequencies, though, will it absorb, okay? Now, a lot of frequencies are coupled together, it gets complicated, but that's the basic idea. And then what do we mean by theta bond angles or bond bends? Okay, so this is stretch, this is bend. Theta angle is what? This bond angle. So that's 3. So my chest is 1 atom, and then my 2 fists are the other 2 atoms. So there's the angle deformation, right? Okay, so 109.5 being compressed or being elongated a little bit, okay? That's easier to do. That will be on the lower end. This is on the higher end. So let me give you the basics of IR now. In the x-axis, we're going to have 4,000 down here to about 1,200, and this is going to be inverse centimeters. This is a wacky unit. We'll get into that in a second. This is where the bond lengths, or the stretches are occurring. Below this, and the units end up at about 400 inverse centimeters, up to 1,200. This is where the bond bends are occurring, okay? Now, what about this unit right here? Centimeters, inverse centimeters, or centimeters in the denominator. Let's define that while we're at the board here real quick. So, in the old days, we had lambda values reported for IR. In the old days, these were called microns. Or what, 10 to the minus 6 meters, and that's about the region of lambda that corresponds to IR. That's kind of clunky because it's inversely proportional to energy. They wanted something that was directly proportional to energy, so they defined this unit, nu bar. And that's kind of a crazy unit too, which was 1 over microns, or 1 over lambda, and again it's related via the speed of light, whatever. But they wanted something that was directly proportional. So you see 1 over lambda, that's what? Distance in the denominator. So they came up with what? Inverse centimeters, which relates to this and has it directly proportional to energy then. And that's how we ended up with Cm to the minus 1 power, whatever you want to call it. Okay, so inverse centimeters, that's what we call it. And that's what? The x-axis here. Bond lengths are in this region, 4,000 to 1,200. 1,200 on down is the bond bendings. And what's the y? The y is transmission. So it's up here at 0, and it comes down here as it's absorbing. Well, now 100% would be up here where it's not absorbing at all, and then 0 is down here where it's absorbing everything or transmitting almost nothing. So here's a signal where it's actually undergoing a bond length distortion, okay? And it's not transmitting very much, okay? So the y-axis is here, so that's kind of the intensity of that. We'll talk a little bit more about that. Let's get back up to the thing there. So there's our basic analytical deal. Sorry, here's the types of spectroscopy. Don't want to go over this. We're talking about IR right here, which is what we're focused on. But you can see some others here, X-ray, UV vis. Maybe you've heard about that. That's polymines and aromatic compounds and molecular orbital energies. as the electrons are excited to different excited states, homo-lumo excitation. Then we got NMR way down here, and that's for chapter 14 coming up. Those will be radio waves. That has to do with nuclear spins, which are very low energy, very long wavelength thing. Then we have microwave for dihedral angles, the rotation gauche and anti and all that good stuff. Eclipse rotation, that's microwave spectroscopy. Right now we're talking about IR for the functional group. So let's get right into it. Jump right in and see a molecule. So here we got propanol. And what do we see here? Down here, you see this big, broad thing. Wow, an OH group at about 3,300 inverse centimeters. And it's very broad in here. That's an OH. And it's higher energy-wise. So that's a very strong bond, OH bond. Look, carbon-hydrogen bonds are a little bit weaker, so they're to the right, and they're a little bit sharper here. We need to talk about why that is, but the strength of a bond has to do with the position here, and then the intensity actually has to do with the change in the dipole moment as that begins to oscillate. Then we have way down here, around 1,000 or so, at least below 1,200 right here. This is the bond angle bending region. This is called the fingerprint region. There's a lot of coupled harmonics here. We don't try to interpret too much down there. There are patterns that can be interpreted, but up here is where we see the functional groups. And those are pretty simple functional groups. The OH group, if you see a big broad thing at 3,300, you probably have an alcohol or an OH group. If you see these little sharp things at about 2,900, those are alkyl CH stretches going on there. So we're talking about stretching, bond length, deformations there. What are the factors that control this position here? Well, it has to do with how strong these bonds are. Carbon-hydrogen, oxygen-hydrogen, nitrogen-hydrogen. They're in general very stable bonds, and they're light here, okay? This is by Hooke's law. I don't think I'll draw it on the board. It's actually in your book. You can look at that, but part of the dependency here of what frequency it is smaller the atom is, and by Hooke's law, the mass is in the denominator there. And you can kind of see from that equation, if you have lighter atoms involved, usually they're at higher frequencies. So here's two heavier atoms, carbon-carbon triple bond to nitrogen, also very stable bonds, so they're up here a little bit higher than the double bonds and the single bonds. So that's what you can see there. Now the intensity has to do with the change in the dipole moment. So carbon-oxygen, carbonyl stretch here, for example, deformation of that bond length, changes the dipole moment dramatically within the molecule. Deformation of about 5% changes the dipole moment, which has directionality associated with it, by up to 1 or 2 debye units. So that has to do with intensity. We'll see carbonyls, ketones being very intense. These single bonds down here are in the fingerprint region, which tend to be very complex, coupled to other harmonic vibrations, which we don't need to worry about. So here's a couple molecules. What do we see here? We see a lot of alkyl stretch, CH here, about 2,900, and a lot of carbon-hydrogen bonds here. And we see the diagnostic carbonyl stretch here, which is always around 1,700, okay? Right there, and it tends to be quite intense. So if you see something right there, that's fine. This is an anomaly from the spectra here, and then this very fine pattern in the fingerprint region. Don't worry about interpreting that. But there is one comparison here we can do between a ketone and an ester. An ester has a carbon-oxygen single bond stretch also, which tends to be around 1,200. And you see it right there. It's kind of broad, and it's not present here in the ketone one. The ketone is the carbon-oxygen double bond stretch. Carbonyl, which is 1,700 right there. That double bond, bond order is 2 here. The bond order is 1 right here on this side, and that's what we see that's a little bit different there. And they have different masses too. We could use the mass spec to tell those two apart. So anyway, that gives you there, but you couldn't tell much else. You couldn't tell the overall structure. So here are the important IR absorptions that we expect you to know. OH, like I said, for an alcohol or a carboxylic acid, those also have OH. Very strong, and they're very broad. Why do you think they're broadened? Hydrogen bonding, that's right. They can interact with other lone pairs nearby and give a lot of different oscillation states to that molecule. So it tends to broaden out the signal quite a bit. Amines are also up in that region. They're a lot less intense. I would list them as small for amines. You don't change the dipole moment much there. Carbon hydrogen don't change the dipole moment either, but they're big. They're strong peaks. Why? Because there's a lot of carbon hydrogen bonds, so they add up, you could say. It also depends on hybridization. If it's an alkyl CH, it's about 3,000. If it's an sp2, an alkene, it's higher. It's above 3,000. And if it's on an alkyne, a terminal alkyne, it's at 3,300. It's a very sharp little peak. But you also see the carbon-carbon triple bond stretch, which is 2250. Then the nitrile one, 2250. These are some you should keep in mind. Certainly the alcohol, the CH1, and the carbonyl one. That's probably enough. You'll kind of memorize them as they go along. And I'll have a data sheet for test 4 also. You'll see some of the characteristic iron. And if there's another one, we'll give it to you there. Let's just go through some of the examples and work a couple problems here at the end. And that'll be it for today. So let's see an alkane. Here's hexane. All we see is the CH stuff. Don't overinterpret this. This is a carbon-carbon stretch, which is further down here. And then we have, what, an alkene. There's that little bit of alkene, sp2 stretch. And then we see the carbon-carbon double bond stretch, which is right about 15 or so. And then the hexyne one. This is kind of diagnostic. Here is the sp terminal alkyne up here at 32 or so. And then the carbon-carbon triple bond thing. And we also have sp3 hydrogens there. So they're different. We can tell these apart from each other. We can't really give the overall structure unless we use mass spec and NMR. Okay. Here's a couple more. Butanol, 2-butanol. See the big alcohol OH guy and not much else. Here's butanone, a ketone. We don't see the big OH anymore. It's not there. It's the carbonyl now. We see 1700. And the ether here. We see the strong carbon-oxygen stretch there and some alkyl CH stretch. But that's all we see. Okay, so stretching those bond lengths, stretches or frequencies or whatever you want to call them, you're okay with either term. Maybe I keep mixing that up. Here's an amine. You can kind of see the amine here. This is a primary amine. It has kind of two little peaks there. And that's for the symmetric and the unsymmetric stretching going on. I could show you that with a little dance here, but that's where the two hydrogens are going out together, or one's coming in, one's going out. Okay, the symmetric, unsymmetric stretch. And CHs, that's about all we got. The amide here, the carbonyl of an amide, due to resonance, there's lone pair here, which lowers the bond order. Draw the resonance structure here. There's a lone pair right there. Put that down and put a double bond here between carbon and nitrogen. Then you have a single bond-like character between the carbon and the oxygen. Okay? When that resonance structure lowers the bond order, which makes this frequency drop down. Often amides are down here around 16 or 1620, whereas a normal carbonyl is up here at 17. And that little bit of a change, we can often tell an amide from a ketone or an aldehyde. And then we got the nitrile here. You see it stands out right there at 2200, and there's no terminal CH stretch, so it's not an alkyne, terminal alkyne. It's a nitrile there. And we can look at the mass spec. This would have an odd mass in the mass spec. So there's other things we can look at if we got the one nitrogen there. So here we got a couple compounds. Look at those. One of these compounds is a ketone. See if you can figure out which one is a ketone. And the other compound is a nitrile with a CN double bond and an amine, an NH2 group. Okay, so one is a ketone. It's actually acetone. I'll give you the name of the ketone. I don't need to draw the structure. I think you could draw acetone, right? 2-propanone. And the other is an amine, primary amine, with a nitrile, a carbon-nitrogen triple bond. Which is which? Which do you think? Compound A. Is this the ketone or is this the nitrile amine? And what gives it away? What can you tell her? Well, they both have CH stretch. That's not going to help you out at 2900. But what do you see here? 1700. So compound A is indeed what? The ketone, right? And that's because you can see the 1700 stretch there for carbonyl. This is acetone, the structure. So the other one by default must be the amine. You see the two little guys here for the amine, and you see the nitrile peak at 2200 right there. And you don't see the big carbonyl. It's missing at 1700. Okay? So this is not a ketone. This one is. Okay? So that's about all you can tell there. You can tell some comparison, and you can rule in and rule out different functional groups. That's all we get from IR. I really want to skip over this. You can read about this, the correct structure of penicillins right here, which is an amide. But because it's a 4-membered ring amide, it doesn't have the same amount of resonance stability. A normal amide down here is 1670 inverse centimeters, which is lower than a typical ketone or ester. And that's because of this resonance lowering the bond order there. And this is lower resonance stability, and this is where penicillin resonates, 1750, which at first made them think it's just a simple ketone. But it's not. It is an amide indeed, but because of the small ring here, it has a much higher frequency for that stretch. And there's some things you can read about there, but we don't have time to do that. We want to look at some applications and a couple problems real quick on IR. So here's a reaction. If we took the IR of this alcohol here, leading to periplanone, this is the cockroach pheromone. This reaction was actually done. IR can be used to determine whether the reaction's done or not by the disappearance of the OH peak, which is at 3,300 inverse centimeters for this secondary alcohol. That will resonate or stretch at 3,300. And if we oxidize it with the chromium-6, chromium oxide or chromic acid like we talked about last time, that'll become oxidized to the ketone, and that will disappear. And what will appear in the IR will be a 1700 peak for the carbonyl. So those two very diagnostic peaks can be used to determine the reactivity of a molecule shown there. All right, so here's a problem. Let's do this problem here. We're given two compounds, or no, we're given data for a single compound here. And the compound X is unknown, and I'll write some of the data on the board here, and I'm sorry, Isaac, we'll kind of go back and forth here. But you can see some of the data here. I'll write it on the board again. The mass spec shows a parent ion, the molecular ion of 88, okay? And that's about all. We won't interpret the fragments. Well, maybe at the end we'll look at a fragment to try to nail something down. And then here's the IR that we see here. We see some CH stretch, and oh, look at this 1700. So what might we have? We've got alkyl, CH, and we've got 1700, so we've got what? A carbonyl. So we might have what? A ketone or an aldehyde or an ester or whatever. A lot of function groups have carbonyls, but there it is. The fingerprint region down here, the bending region, is difficult to interpret. It's exact for a specific compound. It can be used to compare and determine whether you have that exact compound, but it's very difficult to interpret the signals in the fingerprint region. So we'll stay out of that region. But we'll look at the carbonyl and the CH here and this 88. So let's go to the board and figure out what we can do here. So what do we got data-wise? We just have the mass spec, and we've got the ion, and can we come up with a structure? So mass spec gives us 88 mass to charge, and there's this base peak of 57. Maybe we'll get back to that, okay? But this is our molecular ion, we're told. And then IR, what do we have there? We have no OH. Why? Because there's nothing at 3,300, no big broad peak. So we don't have an alcohol, we don't have a carboxylic acid. That's what that tells us. We've got a lot of CH, yep, and we've got carbonyl. And that is it, okay? So what do we start with here? Well, we've got 88. So 88, how many carbons are we talking about here? Well, we could have maybe 6 carbons. What would that give us? 6 would give us up to 72. And what would we need? We'd need 16 more to get to that. That's not the H16. Wait a minute, that's beyond the max, right? So that wouldn't work. What if we had C6 and O? Well, that would leave us no hydrogens. So that's probably not a reasonable structure either. Let's see, what could we get to? Oh, how about C5? So if we had C5, that's what? 60 here, right? And then 60, and to get up to 88, we need what? 28 hydrogen? Okay, probably not gonna happen. Well, we've got a carbonyl, so we have at least one oxygen, right? So maybe let's figure that out. So C5O, so that gives us what, 60? And then how much for oxygen? 16. So it's 76. And so how many hydrogens do we need? Oh, 12. That's perfect, right? Does this add up to 88? Is that consistent with the mass spec? Yeah. So we'd be golden there. Ah, is there a problem though with this formula? What do you see the problem being here? It's 88, it does add up, but is it consistent with the IR? Yeah, it could be an alcohol, and yeah, a lot of CH. Ah, but could it be a carbonyl? What do we need there? We need 1 unit of unsaturation, right? 1 degree of unsaturation, we call it. And there's our 1 degree, right? And so we would have to have less than that. Ah, so that can't be it. Can't be C5, H12O. How about C4? So you kind of keep trying this, right? C4 would be what, 48? So we need 40 more here. And to get up there, we probably have 2 oxygens there. And 2 oxygens would be plus 32 atomic mass units. So what are we up to at that point? We're up to 80, which is good. And then we only need what? What? We need H8. And that adds up. I think you can see that. Here we get up to 48, up to 80, and then 88. So yeah, that's probably it. And are we unsaturated, at least 1 unit of unsaturation? Yeah, so 4 would be 4 times 2, plus 2 would be 10 max. And yeah, we have 1 unit of unsaturation, okay? So let's propose some structures. What do we got for C4, O2, H8? And then we'll go back, of course, and examine the data and see what we got. So we could have this type of thing. That's called ethyl acetate. Does that have 4 carbons? Yeah. 2 oxygens, and how many hydrogens? 2, 3, 4, 5, 6, 7, 8. Yeah, that checks out. Are there other ways to arrange, though, these atoms? Well, we could have this type of an ester. Okay. That's propyl formate. And again, that's just switching over here. You can add that up and see that that one would be okay. And there are actually many others here we could propose. How about this one? This would be methyl propionate, which is a different type of ester than this one, but it's the same ratio of atoms. Are there some other things we could have? Yeah, we could have like a ketone over here and like a methyl ether over there. We don't know. So all of these would be consistent with this data. Notice we have no alcohols. We can't form one of those in a structure. But we're 88 here. Now the only thing we might be able to hang our hat on is right there, this 57 peak. And there's one of these that will fragment such that it'll give a base peak of 57. The others won't. Yeah.
I think you have an extra carbon on that methyl.
Which one here?
Methyl ether.
1, 2, 3, 4. Oh, yeah. Sorry.
Yeah, that's okay.
So I think I need it here. Did that get rid of it? 1, 2, 3, 4, 5.
Take away the carbon.
Oh, take away that one.
Yeah. Yeah.
Okay. Yeah. Thank you, Isaac. That's why Isaac's here. Not only to work the camera, but to all of those. You can add them up, see it's consistent with the data. But the last thing I wanted to say is, let's see. So this fragmentation. Let's go back up to the data there. No, well maybe let me fragment the one that is actually correct. If that one fragments and gives us a psyllium ion via the fragmentation, that adds up to 57. And this acylium ion is actually resonance stabilized, and that's why it's the base peak. So let's go back up to the data real quick, just to wrap up here. And let's see, I think this problem is in the back of your book. I forget the number of it, I didn't write it down. There's a lot of problems like this in the back of the book that use mass spec and IR to figure it out. So there's our 88 thing, here's our 57 fragment that I just showed you, that acylium ion. Here's the carbonyl, and here's the CH. No OH here, no triple bond, nothing there. So this data is consistent completely with this methyl propionate ester, the one that we showed there. So very good. There's a couple other problems. Maybe before we start mass spec, we'll do a couple of those. Well, we've done everything now in this chapter, chapter 13. So your homework is due tonight. Sorry about that. Sorry about the length of this video. It's a little bit longer, but I think we got through it okay. We'll be starting mass spec. We have 3 class periods for that. We're starting NMR, sorry. We'll start that next time. So very good. Take care, and we'll see you again.